have a coil like this, and then if you bring some kind of a magnet, right, when the magnetic flux is changing here, you will see the light glowing, but still the voltage is very, very small, so maybe it's hard for me to make this bulb glow. Instead, we will connect it to a galvanometer, right? That is your first experiment, right? And then we did changing the current in the other coil, right? So this is another coil, so the current is changing here, the magnetic flux associated with this will also be changing, right? So we saw that if the current here is changing, the magnetic flux is also changing, which means there will be some induced EMF in this coil, right? So we saw there is some galvanometer deflection or some LED bulb glowing. Is that clear? What was the third one? Third experiment. On and off, right? When you switch it on and off on this coil, right, you will see some deflection. But when the flow of current is steady, you will not see any deflection on this side. Why? Even though there is some magnetic flux, it's not changing, right? Which means that the current is produced only when there is a change in magnetic flux. Otherwise, there is no current produced, right? So they will ask you a conceptual question, why there is no change in galvanometer deflection when there is constant current flow. Okay, so you should know this. So that was the first thing. And then what is Faraday's law? E is equal to EMF induced is equal to d phi by dt. What is phi? B dot A. B vector dot A vector, right? So BA cos theta. So what it means is, I can change the magnetic flux by changing the magnetic field, or I can be changing the area, or I can be changing the theta angle. So three things, right? So changing the magnetic field means I can take a magnet like this. So let's say I had some small magnets here, right? So I can bring in and out, which means I will be changing the magnetic field, and I saw some deflection in the galvanometer, right? So that is, B is changing. What about A changing? Have we discussed anything where area changing? Did we discuss anything anywhere? Motional EMF, right? What did we do? We moved a rod, right? So you had something like a So remember, you had something like this, and then you are moving this one, right? So when you are changing this, is the magnetic field changing? No, right? What is changing? It's the area associated here. So when the area is changing, right, we saw some EMF generated across this. So that is your motional EMF. Okay. So what was the second block? Eddy currents. So what do you mean by eddy currents? So this is a properly connected conductor, right, in the case of coil and all, right? So in that case you saw the electricity generated in a proper path. Whereas when you have something like a plate, right? So I just have a simple copper plate and I have a magnet. So how did we explain this? Anybody? So as it is coming in here, the magnetic field here is changing, right? So the magnetic field in this conductor is changing, right? So what did we study earlier? Whenever there is a conductor and whenever there is a changing magnetic field, there is a current induced. But that was in a proper wire. But this is not a proper wire, it's just a plate, right? So when you bring this magnet very close to this, there is some changing magnetic field. But one of the scientists called Foucault, what he discovered was, he said that there is some kind of current produced in this plate, right, which is called eddy currents. So it's something like, so suppose if I take this as a plate, the copper plate, and this as the magnetic pendulum, right? Let's say this is north. So as it is coming in here, right, the magnetic field is changing. So what he said was, there is some current produced in here in the way of like swirls. This swirls is called eddies. In the case of water, right? In fluid mechanics, you'll be studying later. So this is called eddies. Okay, something which is kind of swirling around. So when this is coming, right, according to Lenz law, this will also try to become north. If this is north, this will also become north. So north means, if you think about that, it will look like this. So I think it should be in the opposite direction. So I told you north means write the north here and then put the arrow like this, like a curve. Okay, so that means it will go like this. This is what we studied in Lenz law. Okay, Hariharan, can you tell me what is Lenz law? Jevin? Yeah, keep sitting. How long have you been studying this? That and all I don't know. We have finished it. So Lenz law says that whatever change is happening, right, it will try to oppose it. Okay, so go back and study the keywords. So if this is coming in as north, this will also try to become north, which means it will try to reduce the speed, right? So that's why you are seeing that it is getting arrested. And when it is on this side, right, as it is trying to go out, this is north, and what will happen here? It will produce some currents in such a way that it is south. Why? It doesn't like to leave this, because whatever change is happening, it will oppose it, which means when it is trying to go out, I want to pull it back, right? And that is possible only if it is south, which means the current will be this way. So this is anti-clockwise, this is clockwise. So you should know this north and south convention, how to draw this. So north means write it like this, so that you can write the direction like this. This is north. South means write like a simple S, and then this will be the current direction. Okay. So this is for your understanding of what is the experiment which we did here. But then for the exam purpose, I gave you the one which is given in your book. So I think it was something like, the book they are given something different, slightly different, but the same concept. So I think it was something like, this is a north magnet, and then there is a south magnet here, and then there is a plate here which is coming in here, right? So when this is coming in, if this was north and this is south, then this side will try to become north. Okay. So in this case, what we did was we kept the magnet moving around. We kept the conductor stationary. Here in the book, what they have shown us, they have a conductor plate, like a copper plate or something, which is oscillating. And then you are oscillating between the north and south, which means there is a magnetic field. Are you following what I am saying? Okay. So I just showed you only for understanding, but here in the book, it's better to follow the book method. So this is north, this will also become north. So you see how I am writing. So you have to write the north like this, and then you have to say, as it comes in, the eddy currents are flowing this way. Okay, are you understanding? So eddy currents means it's not flowing in a proper path. It's just produced there and then it is getting dissipated. It's not useful for anything, right? Using the eddy currents, can you make a bulb glow? No. The currents are produced there, but it's not flowing in a proper direction. Only when it is produced from plus to minus in a proper direction, right? And if you put a bulb in between, you can see the bulb glowing, right? This is like when and there is some current produced. So it is like a heat dissipation. So the energy is getting converted to eddy currents, and the eddy currents is wasting the heat, or it is dissipating the energy in the form of heat. You following what I am saying? Okay. So eddy currents, is it desirable or undesirable? Desirable in some cases, undesirable in some other cases, right? Can you tell me any desirable case? Electromagnetic train, damping, electromagnetic damping, where is it used? Galvanometer, right? So we said inside the galvanometer you saw a small core, right? So we we said that inside this thing, if you remember, I showed you this in the galvanometer. So inside there was a small black material. That is the core, right? In that core, some eddy currents are generated. So when the pointer is moving like this, right? Sometimes have you seen this? It will do some kind of a vibration, and that vibration is not good. You have to arrest that vibration very quickly. To arrest that, they are saying that there is some core material, a conductor material as a core, and the eddy currents are generated inside this, right? So as the eddy currents are generated here, it will dissipate some of the energy, just like what you saw here. So as you oscillate, it is kind of arresting the oscillation very quickly. Okay, they are not given too much of details, but they will ask you some example questions, right? They will ask you give an example. Okay. And any other desirable case? Induction furnace, very good. Anything else? Magnetic trains, braking of automobiles, yeah. So same like electromagnetic trains, braking for electromagnetic trains. Okay. So what is the biggest advantage? Braking. You will not have any vibrations. Very good. Why? Because there is no contact, right? You see, when we are stopping this, was a copper rod and this one, was it touching each other? No, right? The same principle is used in the electromagnetic trains. So what they say is, when you activate the brake, right? So the electromagnets are coming closer to the, let's imagine this is the rail, right? So as you activate the brake, right? So the electromagnets are going to come closer, which means, so the train is moving at high speed, right? So as it comes closer, this is a magnet and this is a rail. So that means you are going to be generating some eddy currents, because magnetic field is changing, because it's moving at a very high speed, right? Let's say 60 km per hour or 100 kilometers per hour, right? So that means the eddy currents will also be higher, right? So higher the speed, higher the eddy currents, which means it will be generating the eddy currents, and eddy currents means dissipation of energy, which means it will dissipate the energy. So the kinetic energy of the train is converted into heat energy, which can be dissipated in the rail, which means it will come to a stop very quickly. Okay, they are not given too much of diagrams or anything, it's just a small paragraph. So as far as eddy currents goes, I asked you to read it in the textbook. Okay, so I think I gave you the page number also, so read it in the textbook. There is one more situation where eddy currents, okay, I think he said induction furnace. So what is induction furnace? Melting of metals to produce alloys, right? So you put a lot of metals and then you heat it up to produce alloys. So that is what is the induction furnace. But the principle is, you are producing some, as I have been telling you, so it's not, they are not given any diagrams or anything, but let's assume that this is a furnace and there is some lot of coils around this. So around the coils I am sending some AC current, alternating current. Okay. Instead of DC current, it is alternating current. So alternating current means the current is continuously changing. So you remember I told you alternating current means it goes like this. So it's continuously changing, which means magnetic flux is also continuously changing. So if the magnetic flux is continuously changing, what can you say about the metal pieces inside there? Will it be producing some eddy currents there, right? So as the magnetic flux is changing here, there will be some eddy currents produced in this metal pieces, which means they will be getting some heat. Eddy currents is nothing but dissipation of energy in the form of heat. Okay, are you following what I am saying? Okay, try to make some kind of drawings for this. Okay, only then it will make sense, because in the book they are not given any diagrams. Okay, so this is a furnace, this is a coils, AC coils, and this is like metal pieces. So the eddy currents will be produced in the metal pieces, which means it will get very hot, which means it will be melting. Okay, that's the principle of induction furnace.